Okay, if we have two objects, then you got the mass of the boy, the mass of the cart, the total mass of the object altogether is 40 plus 120, that's the 160. Now, we draw a free body diagram. Our weight is equal to mg, which is 160 kg times negative 9.8 meters per second squared. So our weight is equal to a negative number newtons. Now, equal and opposite is our normal force. Since we're on a flat surface, whatever the normal force is, whatever the weight is, that's what the normal force is. So we're going 160 times 9.8. That's going to give me negative 1568 here and positive 1568 newtons here. That's my weight and my normal force. Now, if I apply a force here, now we have an applied force. Okay? If it is going constant velocity, that means that your friction right here has to be equal to the applied force. Now, how do we find the friction? The friction is equal to mu, that little symbol, times your normal force. So if we say our mu right here was 0.6, notice it doesn't have a unit, then that's going to be 0.6 times the normal force of 1568 newtons. So 1568 times 0.6 will give us a friction of 940.8 newtons. So this is going to be 940.8 newtons, and if it's going at constant velocity, most of this stuff will say constant velocity, then that means that this is going at 940.8 newtons as well. So that, according to Newton's first law, these two cancel out. And when these two cancel out, when they're equal to each other, when Fa is equal to friction, then the sum of the forces on the x-axis is equal to Fa minus friction. Since these two are equal, the sum of the forces on the net force is 0. If the net force is 0, according to Newton's second law, A for the x-axis equals F for the x-axis over m. Well, if this top number is 0, that means that A is 0. So when the forces are balanced, the acceleration on the x-axis is 0. No force means no acceleration. No force means no acceleration. Okay, in situation A, I have a spring right here with a hook on it. And the length of this spring normally is 0.4 meters. But when I hook this mass on it, this spring stretches out now to 0.5. The change in length is 0.5 meters minus 0.4 meters. So the change in length is 0.1 meter. Okay, now here's my free body diagram. I got my weight right here, which you know is mg, and I got my spring force right there. Spring force is a restorative force that's going to pull it up, because when you pull this down, the spring force is going to pull it up. Okay, now here we go. The weight is equal to 0.6 kg times negative 9.8. All right. Now, there's a property of the spring called spring constant. We're going to call it K, lowercase k. Lowercase k is going to equal the weight divided by delta L. So I'm going to have 5.88 newtons divided by 0.10 meters. So my K is going to be this number divided by this number. And so since I just inherently know that dividing by 0.10 will move this decimal over one place, I'm going to say the answer is 58.8 newtons per meter. Okay, now you got a vase with some flowers on a trolley going up, and it's accelerating upward. We got to calculate the value of the magnitude of this acceleration. So first of all, we know that weight equals mg, so that's 20 kg times negative 9.8 meters per second squared. So that's going to give us a weight of negative 196 newtons. Here, we have a tension of 250 newtons positive pulling upward. This is what's important. The difference in length between these vector arrows tells me that there's a net force going up. So what is my net force? My net force is tension minus weight. That's the sum of the forces acting on the y-axis. Now, according to Newton's second law, I need the sum of the forces on the y-axis divided by the mass. So right now, divided by the mass, that's going to equal my acceleration. So I know that my tension is 250 newtons minus my weight, 196 newtons. Okay, subtract that first, and this is on the y-axis, and then I divide it by 20 kg, and that should give me the acceleration. So 250 minus 196 should give me 54 newtons. And I'm going to put that on 20 kg, and so my acceleration on the y-axis is going to equal 54 divided by 20, 2.7 meters per second squared, going upward. Now, let's say you're getting ready to dunk a basketball. You have to push down on the ground. Let's say you push down on the ground with 90 newtons of force. Well, how much force does the ground apply to your foot? Well, according to Newton's third law, it will apply positive 90 newtons. Now, if that's the case, your positive 90 newtons will be the force that pushes you up. So let's say your mass is, say, 60 kg. Okay? So, according to Newton's second law, your acceleration on the y-axis, your acceleration, how fast you will accelerate up, equals the force on the y-axis divided by mass. And so the force on the y-axis that you have now is 90 newtons. Your mass is 60 kg. So your acceleration will be 1.33 meters per second squared up. Okay, now, to find the gravitational force that exists between the Earth and the Moon, between any two objects, all we need is this formula right here, where it says G, the gravitational constant, which is something you'll learn it's always the same, is the mass of this object times and the mass of this object times the mass of this object. So all three of these at the top are multiplied, and then the distance between them is squared. Now you may see R here, but R and D are the same thing. So when I say radius, it's a circle because this is going around the Earth. Okay? So, doesn't matter what letter they use, all that matters is you follow the formula. That's all you gotta do. G is 6.67 times 10 to the negative 11. Mass of Earth, 5.97 times 10 to the 24. Mass of the Moon is 7.35 times 10 to the 22. Okay? Now, after I do that, it's 3.84 times 10 to the 6th. And we're going to square that. Now, the rest is calculated. Okay, now, here we go. For this, we're going to turn the calculator sideways, and we're going to have to use our EE. Now, you may see EE on your calculator, you may see EXP, but all you'll do is say 6.67 EE, hit that button, and type in whatever exponent you have. Now, don't forget, that's negative. Then we're going to say times, see how I turned it into the number it's supposed to be? Now, I'm still multiplying, times 5.97 EE 24, that stays positive, times 7.35 EE 22, and that equals, at the top, 2.9, we'll go 3 times 10 to the 37th power. Now, at the bottom, what we want, clear it up, is 3.84 EE6. It equals, that's what it equals. Now, we're going to take it and we're going to square that number. Let me see, I hope, yep, that was square. So we're going to say 1.47 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 10 to the 13th power. Now, all we have to do is say 2.93 EE37 divided by 1.47 EE13, and that'll give us a number. That number, the force of gravity between Earth and the Moon, is 1.99 times 10 to the 24, and our unit is newtons. Okay? Now, that's it. That's how you calculate that. Everything else will just be a calculation, so follow the formula. Now, let's look at this formula. If I double the mass here, the way this works, if I double the mass, then I double the force. However, if I double the distance, if these two get further away, then since this is inverse, the force gets lower. When this number gets bigger, this gets smaller. But it's square. So if I double this, then this goes down by 4. If I increase this by 3, then this decreases by 9, whatever the square is. Okay, so now, let's say this thing is Earth, and we got core, and we got a satellite traveling around the Earth like that. Okay, so to find the G out here, okay, we're going to need that gravitational number, 6.67 times 10 to the negative 11. Okay, we're going to need the mass of Earth, which is 5.97 times 10 to the 24. And then we're going to need the distance from here to here. So I have to think about the radius here, and then the distance here, and I have to add those up. So let's say I add those up, and they come out to 3.2 times 10 to the 6. And I have to take that, and I have to square it. And that's going to give me G all the way out here, lowercase g. I have to do this for you. It's not going to be 9.8 all the way out there. Now, let's say this is going around the Earth at an angular velocity. So whenever you see this, this is lowercase omega. And this stands for angular velocity. So when we see this unit, we're going to see it in radians per second, not meters per second, radians per second. So the capital T stands for the period of rotation. Okay, so how long does it take that object to rotate around the Earth? That's what we want to find out right here, the time that it takes the object to rotate around the Earth. So if I give you, let's see, an angular velocity of, say, 0.02 radians per second, all you're going to do is say 2 pi, which is basically 6.28 over 0.02. And that will tell you how long it takes the object to spin around the Earth, or around whatever it is, okay? Now, remember this is centripetal acceleration. So, centripetal acceleration, when we talk about going around the circle, centripetal acceleration always points in toward the center of the circle. So, I can find the centripetal acceleration by taking this number right here, 0.02 radians per second, and then I square it, okay? And then I'm going to multiply it times the distance here, between here and there. That's the radius. So let's say 5.3 times 10 to the 6. Just make up a number. So I'm going to square this, multiply it by this, and I should get the centripetal acceleration. Now, centripetal force. Now I'm going fast because here you can just follow the formula. Just remember that this is going to be rad per second, and this is going to be meter, okay? Now, all I'm going to do here, this is the same thing as the centripetal acceleration. I'm just going to multiply it by mass. So my unit here is going to be some number newtons. My unit here is going to be some number meters per second squared, okay? My unit here is going to be some number seconds. And that should be it, guys. Good luck.